Hi there, and thank you for your interest in µD3TN. This video is the third and last part of our µD3TN trilogy. In case you haven't watched the first or second part yet, we strongly recommend watching them beforehand to thoroughly understand the following content. While in the first video we focused on explaining the technical aspects of how our µD3TN implementation works, in the second video we then demonstrated how to download and use µD3TN by going through a basic scenario step by step. In this third video we want to show you the way we make use of µD3TN in our own networking project called REDMARS. First, let me explain the motivation and goals of this project. As you may know from the first video of our trilogy, delay and disruption tolerant networking, or DTN for short, is primarily used in so-called challenge networks. These are networks in which extreme delays or disconnections often occur, such as in space or underwater. While the TCP/IP stack is predominantly used in today's internet architecture, it is however unsuitable for challenge networks, as it requires a continuous, low latency end-to-end connection. Furthermore, our current internet architecture cannot perform proper multi-homing, the practice of connecting a host or computer network to more than one network. In summary, the lack of support for both mobility and multi-homing results from the absence of unambiguous addressing of nodes in the TCP/IP-based protocols. In addition to the aforementioned latency constraints, that is why the TCP/IP stack is out of the question for use in challenge networks. Fortunately, there are other alternatives apart from the present-day Internet Protocol suite, and that's where a currently researched network architecture called RINA comes in. RINA stands for Recursive Internetwork Architecture. The idea behind it was first presented by the Internet pioneer John Day in his book Patterns in Network Architecture, A Return to Fundamentals, published in 2008. RINA has been developed as an alternative to the TCP/IP protocol stack to tackle the many problems that surfaced over the years, for example, its growing complexity. As you can see in the diagram below, the Internet Protocol stack organizes its protocols in 4 different layers. Each layer is responsible for a different task. However, the limitations of this structure have resulted in an ever-increasing number of distinct independent protocols in each layer with little to no commonality. Thus, the architecture became increasingly complex over time, which led to lots of problems. The networks became very difficult to operate and troubleshoot, and more new protocols were being specified and implemented that added little value to the existing architecture. With RINA, on the other hand, the scientists and engineers promoting it want to return to a recursive structure, which manages to provide everything that services require today with just a few protocols. The main idea of RINA is based on the assumption that computer networks can also be seen as stacked layers of inter-process communication, or IPC for short. IPC refers to the mechanisms, provided for instance by the operating system, that allow processes to exchange data. This approach makes it possible for RINA to implement each layer with only a single set of recurring protocols, providing an extremely simple, flexible, and scalable network architecture. Since a detailed explanation of how the recursive internetwork architecture actually works is beyond the scope of the video, I recommend you read this article instead. Unfortunately, RINA never managed to achieve widespread use since the existing internet architecture would have to be completely replaced by it. However, the clean slate approach of RINA with the recursive application of a single protocol stack appears to be an attractive idea for a networking architecture that is still in development. That's why we started REDMARS, which stands for Recursive Disruption Tolerant Mobility Enhanced Networking Architecture Study, to explore to what extent concepts from RINA can be transferred to the domain of delay and disruption tolerant networking. We wanted to design and evaluate a technique to enable scalable routing in DTN based on ideas from RINA, which should be able to drastically reduce the need for routing information by decreasing the knowledge of the network structure required in the individual nodes. Now, let's get to the most important part of the video, which is how we merge ideas from RINA with the DTN domain and the conclusion to which we have come. In the year 2022, we've done several experiments and field tests to prove our approach to be successful, As a basic introduction to our project activities, I will first show you a scenario step by step before explaining the actual approach. Let's say we want to use a drone to take pictures and create a 3D map of a specific area on the planet Mars using photogrammetry. First, let me explain the individual network nodes of our scenario. We have a drone controller, a ground station on Earth, a Mars orbiting relay satellite, another ground station on Mars, and 2 drones. Let's call the first drone Chip and the second one Chap. In our scenario, Chap is responsible for taking the pictures and generating the 3D map. The basic steps are the following. In the first step, we have to configure the flight path of our drone Chap in ground control software. The positioning commands are then transmitted to the satellite via the Earth ground station. The satellite forwards the commands via the Mars ground station to Chip, which finally sends them to Chap. Chap then follows the set path, captures aerial imagery of the target area, and generates a 3D map from these pictures. In the last step, Chap delivers the finished 3D map on the exact same way back to us. We simulated the scenario as follows. To configure the flight path of the drone, we sent a request via the drone controller, which is connected to the internet. The satellite that we used for emulating the Mars link was the OPSAT from the European Space Agency, or ESA for short, which is made available to researchers and scientists to deploy authorized experiments for new protocols, algorithms, and techniques. It receives the bundles via an S-band radio uplink. As I mentioned before, we need 2 ground stations, one on Earth and one on Mars, to communicate with the OPSAT. However, we obviously don't have any technology available on Mars. That's why we've built a dispatcher service which multiplexes the link to simulate different ground stations, even though we only connect to a single ground station, the one provided by the ESA. The dispatcher is connected to the ESA ground station via SSH. The positioning commands are forwarded to and from the dispatcher via the Earth gateway and the Mars gateway. In total, we implemented 3 different so-called scopes using the bundle protocol: the interplanetary network between Earth and Mars, an ad hoc network on the surface of Mars, and an overlay network specific to the experiment. Here, a scope is a set of nodes that share joint topological knowledge so that they can communicate with each other. Our approach based on RINA looks like the following. The colored boxes represent µD3TN instances. µD3TN is used to exchange DTN bundles via convergence layer adapters with other nodes, which implement the bundle protocol. If you've watched our previous videos, you may know that the bundle protocol is used for introducing a so-called bundle layer that is able to operate on top of different underlying protocols which provide their service to the bundle layer via a shim layer called convergence layer. Boxes with the same color are in the same scope. The advantage of splitting the network into different scopes is that we now can significantly reduce the effort involved in exchanging routing information. An item of routing information is, for example, that the OPSAT can be reached via the ESA ground station during a specific time interval. For connecting the scopes, we use BIBE, which stands for Bundle-in-Bundle Encapsulation. As the name suggests, BIBE encapsulates bundles from higher layers into bundles from the current layer, which prevents routing information from spilling into scopes it shouldn't be in. I'll explain to you why that's important with the aid of an example. If there were 8 billion bundle protocol nodes on Earth, it would be fatal to transmit all the routing information via satellites to, let's say, Mars, for several reasons. First of all, the satellites are only reachable to a limited extent and have low data rates. Furthermore, spacecraft certainly have significantly less computing power available than would be necessary to process the constantly changing routing information, as spacecraft must be relatively lightweight to be considered cost-effective. We use bundle-in-bundle encapsulation throughout the whole scenario. Let me explain the first few steps to you. Our initial request looks like the following. The first section of the depicted bundles and packets describes the source. The second part is our destination, and the last part includes the payload, which, in this case, are the positioning commands that we want to forward to CHAP. As you can see, in the end we want to reach the mapping application of CHAP. However, our temporary destination has to be the Earth ground station, as it's a network node on the way between the drone controller and CHAP in the end-to-end scope. That's why in the next step we now encapsulate our request in a TCP/CL packet in order to reach our next destination. Now, the payload of our new packet is the bundle containing our initial request. Whenever a bundle or packet reaches its destination, we can remove the outermost shell. And that's exactly what we do in step 3, as the TCP/CL packet from step 2 has reached its target. The bundle that results from this step is our initial request again. In the 4th step, we now want to reach the Mars ground station. That's why we encapsulate our request bundle in a new bundle directed to the Earth-Mars scope BP node on the Mars ground station. This prevents routing information of the end-to-end scope from spilling into the Earth-Mars scope. This procedure continues until our initial request eventually reaches its target. Finally, what was the result of our efforts? REDMARS started in March 2021 and was completed after 21 months at the end of November 2022. Fortunately, we can proudly say that the goals of REDMARS have been accomplished. With the help of BIBE, we managed to develop a scalable DTN concept that takes up the idea of RINA's recursive structure. In theory, through this approach, it would even be possible to create networks spanning the entire galaxy. With the success of our project, it is also shown that a holistic solution for scalable communication and challenge networks could be achieved in the future. If you have any questions or want to contribute something, do not hesitate to contact us. Of course, we will also be more than happy to help you integrate µD3TN into your own networking project. This is the end of our µD3TN trilogy. However, there will certainly be more exciting content coming in the future. Follow us on LinkedIn to receive updates. Thank you very much for watching and see you next time.